Okay, this is going to be the video for Calc 3, section 16.7 on surface integrals. Now that we know how to parameterize a surface, we're going to be able to integrate over that surface, and we'll be able to integrate either scalars or vectors, same as we did when we went through a 1D path. We're going to break this topic into two videos, but we're going to cover the majority of it in this video. And what I'm going to cover in the second video is how you can use an online TI-92 emulator to emulate using technology to do the double integral to check answers, because we're going to be focusing just on setup of integrals here. But if you want to check answers with something where we've published the answers, for example, the odd problems in the textbook, then if you can just check that by trying your setup integral in technology and seeing if the answer matches, that's a good way to tell if your setup was right. But we're going to focus on all the main ideas in the setup today. All right, so here's the idea. Back in 16.2, we defined a line integral, really should be called a path integral, for scalar functions, initially just for a 2D scalar function. So we said if you had a two-dimensional domain down here, and then you had some sort of a z, which is a function of x and y, so you have scalar numbers that are for every value in the domain x and y, then you could pick a one-dimensional curved path, c, through that, and integrate that along that, right? But what we did was we took this curve and we parameterized it. So we have a parameter domain where we have the single parameter t, right? And then that's parameterized into the space curve into the function domain. So we parameterized to get a position vector, to get the xy position on the curve based on the parameter t. And then there's a different function value, a scalar function value, for each of the places in xy. So we integrate by taking a little one-dimensional area, which was the magnitude of the direction vector, so r prime, and then times dt gave me a little one-dimensional length, right? And then we just multiplied that by the integrand, which was a scalar, and summed that up with a single dimensional integral, right? So that was a line integral along a path where we had just two-dimensional domain, right? And then we ramped it up a little bit and said, okay, you could have three-dimensional domain. We still parameterize this 3D space curve now using a single parameter t, right? And then we could go a distance dt in the parameter domain, and the distance in the along the space curve would be the magnitude of the direction vector, so magnitude of r prime dt. And then if we want to integrate that little piece, integrate a scalar function, which varying with x and y along this path, then we have to take that little width times the different areas, right? Or times the different values. So we integrate the integrand, which is a scalar function, but then times the little length along the domain path, if you want to think of it that way. All right. And so that was the formal definition of a line integral, really a path integral to integrate scalar integrands. Okay, and then we said, okay, what we're going to do is, in the last section, we said we might want to not define a space curve that's one-dimensional. Maybe we want to find a parametric surface, which is what we did in the last section, right? We have a parameter domain that consists of a u and a v, two-dimensional parameter domain, which allows us to map across a two-dimensional parametric surface in the actual 3D domain, right? And then if we wanted to find a little surface area, that little ds there would be, we have to take the direction vectors, which are ru and rv, take the cross product to get the normal, and then take the magnitude, and then take that little magnitude and sum that up over the area, right? So the magnitude of the cross product of the two direction vectors in the parameter domain times the little area dA, again in the parameter domain, and that gives us a little patch of that. And we said in the last section that if we take a double integral of this over the uv domain, we're finding the surface area. Okay, so what we're going to add on here is we're going to take that idea of the little what would be the surface area, the double integral of the cross product, magnitude of the cross product times dA, integrated over the parameter domain. But we're going to be able to integrate something other than just the area itself. So we're going to add in this little integrand, right? And if we're now integrating a scalar integrand, so that scalar integrand represents, say, numbers for every place in the domain, that's like summing up all the numbers on the surface, right? when we did a path integral, it's like summing up all the numbers along the 1D path. Now we're going to do a surface integral to sum up all the numbers along an entire two-dimensional parametrically defined surface. Okay, so it's just like the surface area integral that we did last time, except now we have a scalar integrand to sum things up. Okay. All right, and then we're going to go even further and say, well, is there any reason we have to only sum a scalar? We know that we can also sum vectors, right? And back when we did space curve, right, where we had a one-dimensional space curve parameterized with a single parameter t, we said if we're going through a vector field where we have vectors at every point in the domain, we can define the amount of the vector field at a particular location in the direction by taking f, whatever the vector is at that location, and the dot product with the direction vector. And that would give me the percentage of the vector field that's in the direction of motion along the curve, right? And then we can sum up all those things by summing up f dot r primes, right? And that gives us basically the total amount of, like if you think of this as a force field, the amount of total force in the direction, or maybe the vectors are against it or pushing against, it's the total, say, work going through this field, right? So that is, that's a vector integral, right? Line integral of a vector line integral. And so, of course, we're going to now say that instead of summing up vectors along a one-dimensional path, we could sum all the vectors along a two-dimensional surface, okay? But there's a catch to that, right? If I look at a particular point here, how do I define the direction? Because I still need to take the field vector and figure out what percentage of it is in a direction. So what's the direction for a surface? Okay, so the way it's defined is that the direction is perpendicular to the surface in the direction that the surface is curving outward from. So if we have a surface that's curving in this way, so that outward would be this way, then there's going to be some normal vector in that direction to the surface. And if we can compute that, then we can take the dot product of the field vector with that to find the percentage that's going straight through the surface in the direction that would go outward if it was a sphere. Right? If we have a flat surface, then we say the one that's in the positive z direction is the direction. But mostly we have curves, and so we're always going in the direction that the curve is positive. Okay, so we will be summing something over these little patches, but what we'll be summing is the dot product of f with the normal vector of the surface at that point. But luckily we have a way to calculate that, right? We have a way to calculate that from the r and the RU and RV vectors, okay? So first of all, a little discussion about positively oriented surfaces. So we said that we're going to define as, the problem is, if you have a surface here, there's a normal vector here, but you could also consider the normal vector to be in this direction. So which one do we pick? We pick this one, the one that is curving, that's going outward if the surface is curved. If we happen to have a plane, it's the one that goes in the most positive z direction, okay? Okay, so this right here, that expression can be found by using the RU and RV vectors, right? Because I know that this normal vector is just RU cross RV. And to keep everything the same, because we're already accounting for the surface area in our little ds, we're going to normalize that vector. So the first thing we do is we calculate the RU and RV vectors. We take the cross product and normalize that to get the normalized tangent vector or normal vector to the curve. So it's like a vector that's normal to the surface. It would be perpendicular to the tangent plane that's touching at that surface. And then to get the amount of the force field that's in that direction, we take the dot product of that with that normal vector, and then we just sum this up. Right, so this would usually be written like that. We sum this up over the area. Okay, now because we're summing force, the percentage of the field, vector field that's perpendicular to the surface, we give this a different name. It's called the flux of the field F across the surface S. And so sometimes these things are referred to as flux integrals. Right? They're vector integrals across parametric surfaces, but they're also called flux integrals. All right, so the way we'll define that is that if you have a field and you want to integrate it over a surface that's been parametrized, you're going to really find the dot product of the field with the normal vector to the surface at every point, and then sum that over the S, okay? This normal vector is going to be defined as the cross product of the two direction vectors for the parameterization of the surface, u and v, and then we'll normalize by taking the magnitude. And then actually, given the fact that this ds element is really the little area element, which we know is the area in the parameter domain, the uv, but times the magnitude of the cross product, that's what gave us the area along the actual surface in 3D. Then if you were to say, okay, I'm going to take the dot product of this with this, and then ds, but ds is represented by this, these things cross out. So sometimes people will write this form like this. It's really f and then the dot product with just the cross product of the two vectors here. Actually, there's a bunch of vector symbols missing here. Okay, so this is an easier form. It's just the same thing, except that it's whether or not you put this normalization and you allow it to cross off the part of the ds. Right, so you can think of this as over ds, or you can think of it as integrating over the uv area in the parameter domain and just taking f dot the cross product and not normalizing. So this is what we do in practice. What we do in a case of finding a flux integral is we find our ru and rv, we take the cross product, and then we just directly take the dot product of the field with that result, and then we just do a double integral over the area in the parameter domain. So this is the way we actually in practice compute this thing. All right, we're going to look at some examples, and then we'll do some examples. Some of these are worked out. First, what is physical interpretation of flux? So it's the percentage of the field that's going perpendicularly through the plane. Okay, so imagine you had like a vector field, which was an airflow field. It was the velocity of the air moving, generated, say, by a fan like this. So it's moving to the right. If you oriented a surface like this, right, where it was perfectly perpendicular to the force lines of the layer, then this would have a maximum amount of flux, right, because the force field is going straight through, right, and the dot product will be such that the entire force is perpendicular, so there's a lot of flux going through this, right? But if I took that same field and I oriented it like this, where it was parallel to the direction of flow, then we would have actually a flux of 0, right? The flux here would be 0 because none of that is going through the surface, right? It's a measurement of the amount through the surface, okay? So this would have the minimum flux, which would be 0, okay? You can have negative flux, right? If you define the surface in some way that you're saying outward, like if I had something like this, then this is the direction, and so this is going in that direction, so that would be the maximum flux. If I had a curved surface that was like this, and so this is outward, then all of these force vectors would actually be in the opposite direction, and you would in fact have a negative flux, right? So you can have negative flux. That means that the lines are traversing in a way that's opposite the curvature, right? Because remember we said that the normal vector would be in the positive curvature direction, or the curving outward in the curvature, right? This would just happen to have a flux of 0 because there's nothing going through the surface, okay? So that's the physical interpretation of flux. So summary so far, these are the main definitions, right? If you have a scalar function, right, and you're summing over a parametrized surface, then you're summing an integrand over surface, right? The way we do that is we compute the ru and rv vectors for the parameterization of the surface. We take the magnitude of that and then multiply by dA, which is in the parameter uv space, right? And that gives us the surface area, and then we're simply using a double integral to sum up a scalar value. Okay, that's called a scalar surface integral, or surface integral of a scalar function. If we're taking a surface integral of a vector function, then we have to take the vector field, the dot product with the normal vector defined outward when the surface is curving, which again is computed from the normal vector, okay? Technically what that is it's f dot dn over ds, right? But the n is a normalized version of the RU cross RV. But when we want to sum this over if we go, that's over the surface in the XYZ space, right? But if we want to go over the UV parameter space, it turns out that to go from DS to dA, there's an extra element here that crosses this off. So we only end up having to take F dot the cross product without normalizing. So in fact, we never really do this normalization. This is the way we do this. Okay. All right, now there's some simpler versions of these formulas that come about if you're able to do your parameterization using x and y as the parameters. So if you happen to have something, let me just jump up to that and then we'll go back and look at these, okay? There's a simpler form. If you happen to be able to parameterize using x and y and then write the z as a function of x and y, then it turns out, although I'm going to show this without much definition, that you can simplify. You go through all these calculations, and it turns out that this whole expression here simplifies for a scalar to the scalar, but this part here just simplifies to the square root of the z part of the parameterization partial derivative with respect to x squared plus the z part of the parameterization with respect to y squared plus 1. So this is a little simpler form that you can use if you happen to be able to parameterize z as a function of x and y. Okay? And then the same thing, the vector one, if you're able to parameterize z as a function of x and y, then all this complicated cross product stuff, if you can write the vector field as p, q, and r in the xy directions, it turns out, I'm going to show this without derivation, that you can get a much simpler version of the integrand that builds all of the cross product and everything in the dot product into it. It's just the negative of p, the partial derivative of the z part of the parameterization with respect to x minus q times the partial derivative of the z parameterization with respect to y plus r. Okay, and we'll see examples of this used. So what I want to do next is go through two things that are in the notes. And first, we're going to do it using the general way to do this, which works in all cases. And then we'll go back and redo them using the simpler version. Okay, so here's an example of a scalar function. So we have, we want to integrate yz, which is a scalar function, over a surface. And the surface is going to be the part of the plane x plus y plus z equals 1 that lies in the first octant. Okay, so first we have to parameterize the surface. And in this case, since this is already, we have a formula here, we might as well just parameterize that by solving this for z. So we're going to use x and z as the parameters, right? And that means this is gone here. X and z. And the position vector will be defined on x and z. And then z is 1 minus x minus z. I just took the surface function that was given in the problem and solved for z. All right, so the general way, what we would do is we would then find the tangent vectors, right? So this is like equivalent to r prime, right? But we're solving for x and y. Really, this is ru and rv, but ru is x and rv is y because we chose that parameterization. So to do that, we take the partial derivative of the position vector, right? So the x1 would be 1, the y would be 0, and the z would be negative 1. And then the partial derivative in the y direction, which is our v parameter, is going to be 0, and then 1, and then negative 1. And then we're going to be finding the surface normal vector, okay, which is r cross v, right? So I do my r cross v setup here, 1, 0, negative 1, 0, 1, negative 1. And if you go through the process, you can do this by hand, you'll end up getting the vector 1, 1, 1. So the normal vector here to this surface is 1, 1, 1. Okay, and then I could take the magnitude of that, right, because I need that here for this portion to convert the parameter in the parameterized area into the actual area on the surface. That turns out to be the square root of 1 squared plus 1 squared plus 1 squared is 3, right? So this is going to end up being replaced with a square root of 3. And now we're ready to actually do the integral. So the integral is here, this part is the square root of 3, right? We've got the function, which is yz. It has to be expressed in terms of its parameters, right? So I'm going to have to do something here. It's yz, but our parameters, u was x and v was y. So I have to change this z to be in terms of that, I believe, right? So and that our parameterization was z is therefore 1 minus x minus y. So I must replace this z with 1 minus x minus y, so that everything is in terms of the parameters u and v, which in this case are x and y. And then I'm going to do the dA. This is a double integral over the area in the parameter space, right? But that's also xy. So if you imagine on your graph here, the parameterization was my u was x, my v was y. So my uv parameterization is also just the xy, right? And so I'm covering this region. And so we could decide to cover that in the y direction first, so we could put y first. And then that would be going from y equals 0 to y equals 1 minus x. And then we would slide that arrow back and forth here to cover from x from 0 to 1. So there's the setup, okay? This is for a surface integral, where what we're really doing here is saying, okay, this function here has a whole bunch of numbers here. You know, there's numbers all throughout here, like 1, 2, 5, 7, 4, whatever. And what we're doing is we're summing all those scalar numbers across this surface right here. And if you carefully carry out the integral iteratively, you end up getting that this right here is the value. So this value is the sum of all of those scalar numbers that happen to appear on that surface. Okay? All right, so that is an example doing it that way. Now, let me show you that same example done, except using the simplified version. We said that in this event where we were able to parameterize z, pick x and y as the parameters and parameterize z in terms of that, which we were able to do here, we should be able to then use the simpler version of this. Instead of going through the trouble of finding the r prime and taking the cross product and the magnitude like we just did, we can just jump to this memorized expression, basically, okay? And so let me just do the same one this way, okay? Since we were able to parameterize by saying z is the parameters of x and y, then we can just use this other form, right? This form. So let's start working on what we need there, right? The partial derivative of the z, so let's write it, z is 1 minus x minus y. So the partial derivative of z with respect to x would be -1. Partial derivative of z with respect to y would be -1. And so this little square root becomes the square root of -1 squared plus -1 squared plus 1, which is a much faster way to get to our square root of 3, okay? And then we would have the same setup as before, the same integral. So using this structure, because we happen to have the z parameterization, turned out to be a little less work. But you could always use the more general one, compute the RU and the RV, take the cross product. Just happens to work out that this simpler formula works if you can parameterize z in terms of x and y. Okay, so there's an example completely worked out in the notes of a scalar surface integral. Let's do an example of a vector surface integral. Okay, so let's say that we want to evaluate the surface integral for this vector field, xy, yz, zx. So plugging in different x, y, z values, this gives me different directional force vectors here at every x, y, z. And we want to do this over the part of the paraboloid that is this paraboloid here. So that is a paraboloid that starts at 4 here and opens downward like this, right? But only the part that lies above this square here from x is 0 to 1. So it's a part of this surface here. So I've tried to sketch it more accurately here. This blue surface is a part of this paraboloid, all right? Right. And what we're doing is we want to integrate, however these force vectors are appearing throughout here, we want to integrate the percentage of the force vectors that go perpendicularly through this surface. Okay, and since the surface is curving in this way, it's going to be the portion that's going through the surface in this direction, in the outward direction. So we're summing all the percentage of this field that's going through that. Okay? All right. So the first thing we need to do is parameterize the surface. So again, since we have a function which we could solve for z, we might as well just use x and y as the parameters. Don't know why I put that in there. And then write z as a function of those, right? Because they actually gave it to us that way. So the parameterization will use x and y. Z will be in terms of that. Then we'll find our RU and RV, right? So those are the first partial derivatives with treating x as the vector. That would be 1 and then 0, and then negative 2x. And treating y as the vector would be 0 and 1 and negative 2y. And then we can compute the surface normal vector. So that's the vector that's going to be moving around here as I go to different places. R cross V, if you load those up and you do the procedure, this minus this and so on, you end up getting 2x, 2y, 1. Okay, and so this is not a constant vector like it was in the case of the plane. Here it's changing for the different x and y. That's how we account for the fact that outward is changing, is that's built into the normal vector. Okay, now we have the normal vector. What we do is we just take the field vector and the dot product with the cross product, which this right here is the normal vector. So I'm just going to take the dot product of the force vector with the normal vector, and then we'll sum that up over the parameter domain, which in this case is xy. All right, so first we need to say we got the force vector, and this is the same as the normal vector, which we just computed. So I'll just load those in, take the dot product, which is this times this plus this times this plus this times this. That gives me this. We can simplify that a bit. It ends up simplifying down to this. And then the area, we're just covering the parameter domain, right? So the parameter domain uv is just xy, because that's how we chose to parameterize. And so that means that we're covering this much of the parameter domain uv. So we have to somehow integrate a double integral over that. We could choose to go y first, and that would be going from y equals 0 to y equals 1, constants, and then from x equals 0 to 1. So both limits are 0 to 1. And if you go through the integration, you get a number, okay? And that number represents, even though we're dealing with vectors, remember what that number represents is you've got these normal vectors at each point. I'll draw a couple of them, okay? And you have your force fields, your force vectors, okay? So maybe they are changing like this, okay? So what's happening is at every point, we're taking what percentage of this vector is in this direction. Maybe it's this much. Most of this is in that direction, so this much. And not very much of this field is in this direction, so this much. So it's the sum of all the percentages of the field that are perpendicular to the surface at that point, all summed together, and all of those sum up to this. So you can kind of think of it as if you had a source, say, of water that was flowing in different directions, and you put sort of a net here. How much total water would cross the boundary? This much total water would cross. All right. All right, now because this is a parameterization where z could be written in terms of x and y, we should have been able to also choose the easier version of this. So the easier version of these formulas don't require us to calculate these cross products and things. We just can use this simpler structure. So let's see if that works. What we can do is say, okay, because we have a z, which is also written gxy. For some reason, the book doesn't write this as dz dx. They use dg, but g is just the z parameterization. Again, I don't know why I have that there. So let's find p. Well, so this would be p, q, r, because they gave us the function definition. So p, q, r are just x, y, y, z, and zx. Okay, this partial derivative g with respect to x is just the z, but the partial derivative with respect to x, which would be negative 2x, right? Partial g with respect to y would be this, but partial derivative with respect to y, which is this. And so if I just plug all that stuff into that simplified formula, the p is xy, the dg dx is negative 2x, the q is yz, and then the r is the zx. And you end up, lo and behold, getting the exact same thing that we got when we did that, where we calculated by hand the r and the g. Okay, I need to look and see what Miss Dastu did on the test as far as formulas, but I think I'm going to probably, whether she did or not, I think I'm going to let you have all the formulas on the test. Just its virtual environment, I think we need to do that. So let me state that, yeah, I'm going to go ahead and allow everybody to have the simplified formulas as well as the complete formulas on the test, so that you don't have to try to memorize these things. No point in that. Okay, and on the test, we're going to be focusing mostly on setup. All right, so let's do a couple more examples, and we'll do setup only, and then I'm going to split off a separate video that goes through how to use a if you have a, well, I'm going to do it with the TI-92, but like TI-89s and Inspires may work similarly. I know that TI-92s and TI-89s work similarly. So I'll show you how you can do double integrals using technology so that while you're practicing homework, you can check answers quickly. Like you can do a setup and then try your integral and then see if that matches the answer in the book. But we'll do that in a separate integral. Let's do some more setups here. Okay, let's say we want to evaluate this surface integral of xy over a surface where the surface is the triangular region with vertices, these three vertices, okay? This is a scalar, so we're going to be doing a scalar surface integral here. So let me make a sketch first to see what's going on. We've got a triangular region. Let's see, I've got the point 1, 0, 0, so 1 for x, 0, 0. Right, there's 1, 0, 0. And then I've got the point 0 and x, 2 for y, 0 for z. So this is 0, 2, 0. Then I've got the point 0 for x, 0 for y, 2 for z. So that's up here, 0, 0, 2. Okay, so there's a triangular region in 3D space. So basically this is a planar surface, right? All right, so this is the surface, and we want to integrate the number values of all these, whatever x times y would be, along all these numbers and get the sum of that. Okay, so first I'm going to need some kind of parameterization of this surface. Okay, we're going to use the method where we take vectors, two vectors, and then we use the normal to find an equation of a plane. So I'm going to build the equation of a plane this way, using ax plus by plus cz equals n dot r0. But I'm going to need a normal vector to this plane, and I can find the normal vector by taking the cross product of two vectors that are in the plane. So let's quickly define a couple vectors. What if we did this? Let's do a vector, this vector, okay? And then I'll take this vector. So actually I'm going to take the vectors all the way across here, but just to kind of not clutter this too much. This vector here, I'm going to call this vector 1. That vector would be this minus this, right? So that's going to be 0 minus 1, 0 minus 0, and 2 minus 0, which would be the vector -1, 0, 2, okay? And then let's take another vector, vector 2, and let's do 0 minus 1, 2 minus 0, 0 minus 0. So that gives me the vector -1, 2, 0. And then I'd like to get a normal vector, but you know what? I'd like for it to come out of the page. So, you know, I'm going to actually take v2 cross v1, because that will give me the vector that's coming out of the page as the normal vector instead of the one going in. It doesn't really matter. Actually, it does matter, I think, because we need to have, for a plane, we said that the normal vector for the surface should be the vector that goes in general towards the positive z, right? We don't have any curvature here, so we can't define an outward shape, so we have to go the one that goes in the positive z direction, and that would be up. So by the right-hand rule, 2 cross 1 here would produce that. So to get my normal vector here, I'm going to go v2 cross v1. Cross v1. Okay, so I've got my plus minus plus. I'll put the 2 vector in first, -1, 2, 0, and then -1, 0, 2. And so now I've got, let's see, this is going to be 2 times 2 is 4, minus 0, the negative of -2, minus 0, and then 0 minus -2, so plus 2. And so that would give me 4, let's see, 2, 2, which is the same as 2 times 2, 1, 1, right? So what I'm going to do is use this right here as the normal vector, right? We're going to say the normal to the surface is the vector 2, 1, 1. Doesn't matter what its length is right now. Okay, so let's continue to build the equation. I'm still working on an equation for this surface, right? So now that I know that, let's pick this point as the R0 point, and I'll fill this equation of a plane in. So I've got A, which is 2. This is my ABC while I'm building my plane 2x plus y plus 1z equals 2, 1, 1 dot any point on the surface. I'm going to pick this one, 1, 0, 0, which would be 2 times 1 plus 1 times 0 plus 1 times 0 is 2. So this plane is 2x plus 2y plus z equals 2, right? All right, or if we solve it for z, it's 2 minus 2x minus 2y, right? Okay, and that means if I want to parameterize that surface, I can pick my position vector to be a function of x and y. And so I'm going to just keep x as x and y as y. I'm going to write z as 2 minus 2x minus 2y. Okay, there's my parameterization. Okay, now that I have a parameterization, I can pick one of the forms. So there's two forms for the scalar. I could use this one. I could say that the integral is, so this integral xy is, it's more generally over the domain and the parameter region is going to be f evaluated at r uv, the integrand, and then magnitude of ru cross rv dA, right? That'd be one way. Or I could, because I had this parameterization of z in terms of x and y, I could choose the simpler version, which says that this is just equal to that same function. I could write it as, you know, x, y, and whatever the z is, okay? But then just times this partial z with respect to x squared plus partial z with respect to y squared plus 1. And then integrate that. So I could choose to do this, or I could choose to do this. It doesn't really matter which one. Let's go ahead and use the simpler one on this one. So to do this, I'm just going to take my z here and find these partial derivatives. So partial derivative of z with respect to x would be negative 2, right? Partial z with respect to y would be negative 2. And so I can now just build this. This integral is the double integral of the surface. Now the surface is xy, right? And so the x gets replaced with x, nothing to replace. The y gets replaced with y, nothing to replace. There's the integrand. And then I've got this square root of the partial derivative z with respect to x squared plus the partial z with respect to y squared plus 1. And then we can cover this with either x or y. So let's finish the setup. The parameter domain is xy, right? Because u is x and v is y. And so that means I'm going to be covering this over this region. So it looks like I've got a triangle here. And this goes out to 1 in the x direction, right? But it goes up here to 2 in the y direction. So I think I've got that right there to cover. So let's pick a parameterization, or let's pick a direction. Maybe we'll go y first and then x. So we'll go y first. That means we're going to go from y equals 0 down here to this curve, which is y equals 2 minus, and then what is that? A slope of negative 2 minus 2x. So this will be from 0 to 2 minus 2x. And then we have to slide over here from 0 to 1 in the x direction. All right, just maybe simplifying this a little bit more, I could write this as 0 to 1 for the x, 0 to 2 minus 2x for the y, xy is the integrand, and then this just going to be 4 plus 4, which is 8, plus 1 is 9. The square root of 9 is just, is that right? Wait a second. 2 squared, yeah, is, oh, sorry, I made a mistake here. This is dy dz dy. No, that's right. That's right. So actually my answer key that I currently have posted, I'll try to fix this and post it again, is wrong. So this actually would be 4 plus 4 is 8 plus 1 is 9. Square root of 9 is 3. dy dx. That's the setup. And that's actually simple enough. You could just integrate that by hand if you needed to. Okay. So there is a setup, and we used the simpler version. This was a scalar. Okay. All right, let's take a look at another example. Evaluate the surface integral yz over a surface with these given parametric equations. So this is nice. They gave me parameterizations, and they gave me the region that I'm supposed to integrate over. So all that stuff of parameterizing, I'm not really going to have to do. I'm just going to have to set this up. So let's just go ahead and write it out. The parameterization they gave was in terms of uv this time. So x is u squared, y is u sine v, z is u cosine v. I don't think I even have to bother to graph this, right? Because they went ahead and gave me the parameterizations I need. So let's just keep going with it. And then I'm going to, this is a scalar, right? Now in this case, remember I said I had these two choices that I could use, the simpler version or the complex version? Well, we don't have z written in terms of x and y. So we're going to have to use the more complicated setup here. We're going to have to use this one with the cross products. And that's fine. It's not that much harder. So the way we do that is we take the two partial derivatives of the position vector with respect to the two parameters. So ru in this case, okay, the x component would be 2u. The y component would be the derivative of u is 1 times sine of v. And then here, this is u cosine v, right? So this would be, derivative is 1 times cosine v, right? And then our v would be the partial derivative treating v as the variable. No v here, so that's a constant. This is a constant, but the derivative of sine is cosine, so this is going to be u cosine v. And the derivative of cosine is negative sine, so that's going to be negative u sine v. Okay, so this is the partial derivative. Now we're going to have to compute the cross product of that. Right, the cross product is plus minus plus 2u sine v cosine v, 0 u cosine v negative u sine v. Okay, so that's going to be, let's see, for the s component, it's this times this, so it's negative u sine squared v, right, minus this times this, which would be u cosine squared v, okay? And then it's the negative of this times this, so that's going to be negative 2u squared sine v, right, minus this times this, which is 0, okay? And then it's this times this, which is 2u cosine v, minus this times this, which is 0. Okay, so carefully finding the cross product here. This is going to be, you know what, I can factor out a negative u here, and I would get sine squared v plus cosine squared v, which means since that's 1 that this is negative u. Here I've got a negative negative, so that's positive 2u squared sine v. And then here I've got 2u cosine v. All right. All right. And then, unfortunately, I believe I have to take the magnitude of this. Yeah, so let's take the magnitude. Ru cross Rv. It's going to be the square root of this squared plus this squared plus this squared. Okay, and so let's get a little bit more room down here. That's going to be, well, maybe I can do it over here. The square root of, this is u squared. And then I've got, let's see, everything is squared in here. So 4u to the 4th sine squared of v plus, let's see, 4u squared cosine squared v, which I believe means here I could factor out of 4u to the 4th, and then that would leave sine squared v plus cosine squared v, but sine squared plus cosine squared is 1, so this ends up being the square root of u squared plus 4u to the 4th. All right, and then what we have to do is take the integral of the integrand times that. So the integrand was yz, okay? So for the y, that's going to have to be replaced. So ryz, the y is replaced with this, because that's the parameterization, u sine v, and then the z has to be replaced with u cosine v, according to what they said. U cosine v, and then we have to put our, go back here to the template here. We have to now plug in our cross product magnitude. We just did that. Now we have to do the cross product magnitude and then the area. The cross product magnitude turned out to be the square root of u squared plus 4u to the fourth, and then we have to use du dv. So this is going to have to cover this in u and v. Okay. I'm just going to put du dv here, and that's because they gave me actually these things, and they're both constants, right? So I'm not going to have to actually sketch this and figure out how to cover one to the other with equations, because they gave me the limits. So because these are constants, I should be able to do this in either order. So u is going to go from 0 to 1. So I'll put the u here from 0 to 1. And then v is from 0 to pi over 2. So that's on the outside, 0 to pi over 2. Those could have been reversed. If there was a dependency, then they would have had to either give me a sketch or some other way to figure out the dependency, or maybe this would have been written in terms of variables. Like one of those would have been variables. Okay, so this is the setup for that, right? Not this part. Okay, that's this setup. All right. And then one last example. Let's do one more. We haven't, these have been both scalar examples. Let's do a vector example. I know this video is getting quite long, but best to cover it all at once. Okay, evaluate the surface integral of a vector field f dot the parameterized surface S for a given vector field, and that's oriented, and the oriented surface, which means it's oriented in some way that they're going to tell us. In other words, find the flux of f across S. If f is given as this, and the surface is given as z equals x e to y. So they gave me an equation that was already parameterized in terms of z and terms of x and y. And then they gave me boundaries actually for x and y. All right, so pretty strong. We want to use x and y as the parameterization here. And they said it's already oriented in an upward orientation. So we're going to calculate it that way. All right, I'm going to use the general version, even though this is the x and y, just so you can see how that works with the r and v, because this will work in all cases. So we're going to use this version to calculate this integral. We're going to say that f dot ds has to be, we're going to end up taking the double integral over the domain area of f, and then we're going to take the dot product with just the normal vector, which itself is going to be the cross product of u and v. Okay? All right, so my parameterization, they gave it to me, pretty much, is that we're going to use x and y, right? Because they gave me the surface z in terms of that. So x is going to stay x, y is going to stay y, but z is going to be x e to the y. So there's the parameterization of the surface. All right. And then that means I'm going to calculate my RU and RV. Those are going to be RX and RY. So what would RU, which is RX, be? Okay, so if I take the R vector and I take the derivative with respect to X, it's 1, 0. And then the derivative here is 1 times e to the y. So that'd be 1, 0 e to the y. Okay, the RV, which in this case is RY, is going to be 0, taking the partial derivative here, 1. And then the derivative here, the x stays here as a constant, but the derivative of e to the y is just a copy e to the y. Okay. All right, so there's my, my derivatives. And now I'll compute the normal vector, r cross v. The normal vector is ru cross rv, in this case x and y. So we'll do our, let's see, we've got our x, which is 1, 0 e to the y, and ry, which is 0, 1, x e to the y, plus minus plus. And so that means we're taking 0 minus e to the y. The negative of this times this is x e to the y minus 0. And then this 1 minus 0. So it looks like we've got negative e to the y, negative x e to the y, and 1. Okay? Right. Now, what I need to do is compute the dot product of f with that. Right? So what is f dot n? Well, f, they gave me, was xy, 4x squared, yz, but I'm going to replace this z with the parameterization, right? The parameterization was that z is really x e to the y. So I'm going to substitute that in right now, x e to the y. That's f parameterized. Dot n, which is negative e to the y, negative x e to the y, 1. So I'll do the dot product. So that's going to be xy times negative e to the y plus 4x squared times negative x e to the y plus yx e to the y times 1, right? Which will be negative xy e to the y minus x to the third, 4x to the third e to the y plus xy e to the y, okay? And then finally, the integral is just to integrate that all over the domain, the parameter domain area. Okay, so we have to take the double integral of that, negative xy e to the y minus 4x cubed e to the y plus xy e to the y. And now I have to cover the domain area. Now, luckily, they gave me this, which is nice. They could have given me something where I had to sketch it and figure it out from a picture. But again, I have constant boundaries, so I could do this in either order, and they're both from 0 to 1. So yeah, we usually do y first. Let's do that. Y goes from 0 to 1, x goes from 0 to 1. That's the setup. Okay. In the second video, I'll show you how you can use technology to plug that in all at once in a calculator and see if that matches the answer in a book. All right, so that is it for integrals there, and we'll cover this technology stuff in a second video.